So it is my pleasure to introduce Anisha Shrestha. She worked on a project this summer with Mike Fraker and Russ Miller, and excited to hear about it.
Yeah, thank you, Mary, so much. Hello, everyone. I'm Anisha Shrestha from Grand Valley State University. I recently completed my master's degree in data science and analytics. I have been working in a glider project under Dr. Michael Fraker and Russ Miller. The project is about identifying the most interesting and relevant pattern in the Great Lakes and developing a deployment plan for the glider that maximizes the usefulness of the glider's future data collection. So this is the outline of my project, and if anyone has not seen the glider, so the glider's picture is on the right-hand side. Yeah. Okay, so to start with, I will talk a little bit about the glider, how and what kind of data it collects. Glider are the autonomous underwater vehicle used to collect the spatial and temporal data throughout the entire water column with a multiple sensor. It travels like a straw tooth, and if you see in this first figure here, creating profile each time it goes up and down or change the direction. Unlike buoys, gliders are buoyancy-driven winged vehicles and can be programmed to travel to specific areas of interest in order to collect the environmental data like temperature, conductivity, chlorophyll depth, or some other different kind of parameters. And the glider was deployed in Lake Michigan, Huron, and Ontario since 2012 to 2019. Slocum glider are called GLOS 236. The glider was deployed up to 60 days straight, and it can travel up to 1 kilometer per hour. The depth limit is 200 meters, and its battery could last up to 150 plus days, depending on the type of battery cell. It has different sensors attached to it, like oxygen sensor, optical sensor, similarly power sensor. So power sensor was integrated after 2015, which measures the light. It measures photosynthetically active radiation. Similarly, we have EcoPuke, which is chlorophyll, sedum, backscatter, salinity. And then we have CTD, which means conductivity, temperature, and density. So these are some of the variables collected by the glider. So how much data is in there? There were total 20 deployment made. 2 deployment in 2017 was done in Lake Huron or Saginaw Bay, and 3 deployment, 2 from 2013 and 1 from 2018 was done in Lake Ontario. So the total glider days was 520 plus, and the profile per hour was 5 plus. And as you can see here, after 2015, we have power sensors in the glider. So where did the glider travel? The glider went across Lake Michigan from Muskegon to Milwaukee. If you see in 2014 map, you can see it basically traveled from Muskegon to Milwaukee, and some short transient near Muskegon and some near Milwaukee. So this is the path it traveled on each year. And on the right bottom side, this is the map for 2017, and you can see the deployment was in Lake Huron. So on this image, I have taken from the last year's work, and you can see the graph for each variable. We can use a customized software called Glider Scope in order to generate similar kind of graphs. But we focus on soft surface chlorophyll, like how chlorophyll varies and what physical drivers can be linked to the variation. So I'm basically looking at temperature, chlorophyll, and PAR, and some other values from it. So this is glider data analysis, and these are some of the analysis that we did to see the trend and pattern over the period, focusing on the chlorophyll depth, mixed layer depth, KD, optical depth, and ephotic depth. And I'll talk how I approached for these values. So on this slide, before I go into mixed layer depth, I will talk briefly about stratifications and how when it occurs in the lake. So usually what happens is surface layer of the water is warmed by sun from late spring to late fall, and during this time the surface layer of the water is also mixed by wind, wave, or sometimes it could be by storm. And in the first figure here, we have temperature on the x-axis and depth on the y-axis. And during the winter time, the lake is cold and the overall temperature in the lake is more uniform. And during the spring, we can see the temperature starts to rise, and in summer times the temperature gets high and the lake stratifies into 3 layers of water, which is shown in the top right figure. The upper layer is the warm, lower density, lower nutrients, and at the surface, and this is where the middle layer. There is this middle layer which is characterized by the steep gradient in the temperature, and this layer is called thermocline. The deepest layer with uniformly cold water that does not mix with the upper layer is called deep layer or deep water, and the mixed layer here is the layer above the thermocline. Thus, the beginning of the change where the surface temperature cools by 0.5 degree is called the mixed layer. And there are a lot of ways to calculate the mixed layer, like some use 0.2 degree cooler Celsius values, or some use slope, but here I have used 0.5 degree cooler values. This two figure below also, as you can see how surface temperature increases from June through July and becomes increasingly stratified till late fall. And around November, the temperature starts to drop. This is the process how stratification occurs in the lake. Moving on, well, in order to calculate the mixed layer depth, the initial steps were binning the data into 2-meter depth and calculating the average for each bin. The surface temperature is the aggregated value for from 0 to 6 meter. So this is the, the surface temperature here is what we are comparing with. The figure below is the mixed layer depth for 2019, September to October. On the x-axis, we have profile ID, and on the y-axis, we have depth. And you can see the dots. These are the 0.5 degree cooler points. There are some points which are a little way deeper than expected, around 40 to 50 meter or so, but these are some of the outliers, and we have filtered out these values while getting the mixed layer depth. On this graph, so mixed layer depth is usually around 10 meter during the starting of the summer, around July, and it gets deeper early in the year, early and late in the year. So this is caused by stratification during the summer and turnover in the year, and the depth goes deeper over the end of October or starting of November. So this is what I wanted to highlight, the trend here for the mixed layer depth. These are the yearly trend for the glider data that we have. The red lines are the slope and the dots are the 0.5 degree cooler points, and all the results are like what we expected to see, except some. If you see in 2013, 14, 15, it's kind of showing the pattern, but sometimes it might be deeper in the middle of the year because of the change in wind strength, but we might also not get a relationship. The line around 2016 on the top right, as you can see, it's straight towards the end of September, which could be the missing data. And while we look at 2018 or 19, there is a fluctuation in the trend, and exploring more about the possible reason what could be. So we took the buoy data, and this is the buoy station, and it was located near Muskegon, and this is the buoy picture on the top left. So we use wind direction, wind speed, and water temperature with mixed layer depth to create a regression model and see if there is any significant values or not. And the result shows water temperature was slightly significant in 2014, around July through August. And then similarly, we also have significant value for wind direction on 2018 from May to April. And from the NOAA website also, there was an evidence of high wind and severe storm in May 4, 2018 on the southwest side of Michigan, which might be one of the reason in fluctuations in the mixed layer depth. Another variable is KD. KD is the slope of regressions of natural log of power versus water depth. Sorry. Again, people use various other ways to calculate the KD, but this is how I approached it. It is important to understand the mobility of the compound in the water, and we can predict the underwater light climate for the phytoplankton. PAR is commonly used to quantitatively access the light availability. It indicates the ability of solar radiation to penetrate a water column, and here we choose 20 meter to get the value for KD, because as you can see on the right hand side, the presence of light is more within 20 meter depth. However, while getting the measurement of KD in water, there are several other limitations because we are only focusing on light, but the data consists of nighttime, cloudy sky, and which makes it a little difficult to achieve the spatial coverage. And on this figure, these figures are after 2015, as PAR sensors was not before that. The expected value for KD in Lake Michigan is around 0.1 or 0.2, but it can differ. On the y-axis, we have the value of KD, and on the x-axis, we have profile ID. Similarly, if the water is clear, then the KD will be high because the light can penetrate more, and vice versa. The glider's location is also very important, whether it is near shore or offshore. For example, if KD is lower near shore than offshore, the benefic areas near shore might get less light and be less productive than expected if we use KD to measure for the whole lake. So another one is we have chlorophyll layer depth, and which is very important for all the phytoplankton and has a very big effect in ecosystem. As the depth increases with the mixing event, phytoplankton must rely on having a higher pigment counts to capture the photic energy, and getting the chlorophyll layer depth can show how much chlorophyll is in there and how much phytoplankton are present during that time. So the image on the left side is the gyroscope output. The same output is shown in the right hand side with only maximum chlorophyll plus 80% of the maximum chlorophyll in the lake. So this way we can see where the chlorophyll has a very high concentration and where not. The line on the top is the mixed layer depth. Again, we can see the change with the mixed layer and chlorophyll layer together. So on this graph, chlorophyll concentrations increases uniformly at the depth during this summer. The deep chlorophyll layer usually varies around 25 to 40 meters during the summer, but sometimes higher or lower as well. And in the winter, there is not enough light that gets through, so the chlorophyll is around the surface or above 20 meters or so. As you can see, there are some fluctuation in the line around 2018 and 17, and this could be the weather event that occurred in 2018 while doing the regression modeling with chlorophyll layer depth, and it shows wind direction being the significant reason during this time too. But we didn't separate out the glider location yet, so there might be some of the variation like because of the near shore or offshore, and there also might be differences between the north, south, or east and west. This graph is basically I wanted to show the chlorophyll width mainly. The yellow shade around the red lines is the width of the chlorophyll, and this varies in the white region too. Somewhere it is thin and somewhere it is too thick, but we didn't go deeper into this, and this might be something interesting to look after. So lastly, we have these two measurements called optical depth and ephotic depth. The optical depth is how far we can see, and lots of phytoplankton are lower than the optical depth, and the satellite cannot measure that region. Ephotic zone contains a vast majority of plants and animals too, and very less amount of light penetrates beyond that depth. The ephotic depth for the Lake Michigan is around 40 to 60 in this green line, and the deep chlorophyll layer is well below the first optical depth and just above the ephotic depth. And this is important because the satellite measurement only records chlorophyll concentration above the first optical depth. So the glider measurement and satellite complement each other, and the gap in between these points are because we filter out the nighttime and cloudy profile. That is the reason we have a regular interval of gap in the figure. Lastly, this slide shows how these variables are found in the lake, and the first two figures are before 2015 with no PAR sensors, and which is why we don't have optical depth and ephotic zone, as these values are based on PAR. The mixed layer depth is around 20 meters or so in the first figure, and the chlorophyll and mixed layer depth are overlapped. But later on, as we can see on both these layers, around October to November, they are separated and due to stratification. And the second two pictures, we have all these values in the figure, and this is how different values are found in the lake. To sum up, further analyzing this data will help develop plan for targeted glider deployment in the future, aiming at some specific questions. And that way we could plan the deployment in a very specific areas and in a specific time period. We also observe a substantial variation that could be ecologically important. As you can see how all these variables mix up, and we can quantify these values across the lake. future work is one could be separating out the spatial influences like nearshore or offshore on the calculated variables, and similarly another could be looking more into how weather pattern influence the deep chlorophyll layer. And we also have glider data for other lakes too, because all these analysis were only focused for Lake Michigan, and we can run similar analysis and compare it with Lake Michigan. And lastly, I would like to acknowledge my mentors for constant support and guidance, Lauren Marshall for the slides and pictures, CIGLR and Mary for making this fellowship successful and very supportive in everything, Noah and CIGLR for the information on the weather data and other resources. And thank you.
Thanks so much. Thanks so much, Anisha, and wonderful job on your presentation. Really, really cool results that you had. We have a couple of comments in the chat box here, and feel free, anybody else listening that has a comment or question, type them in or go ahead and raise your hand. So Debbie Lee says, excellent work, and looks like she was exiting. I think she was talking to everyone there. So congratulations to everyone there. Ayumi Manome says, great work. The info of mixed layer depth is very valuable for modeling. So thanks for that comment, Ayumi.
Thank you so much.
Okay. All right, and I don't see anything else coming through. Okay, one question here from Hank Vanderplug asks, nice job. Could you explain optical depth?
So optical depth are the depth values that we can see by our naked eyes. And in order to calculate this optical depth, we need this par attributes. So this is how I calculated the optical depth. We have par, and then optical depth is like 1 by kd. So this is basically how far we can see in the water column by our naked eyes.
Okay, thank you for that answer. And Russ Miller, one of your mentors, has a comment. He says, these filtering techniques and code that you've developed should be very useful going forward.
Yes.
So that's good to hear. And Hank says, thank you. So that must have answered his question. Okay, we've got a hand up from Ed Rutherford. So Ed, I'm going to allow you to unmute yourself. So Ed, whenever you're ready to ask your question, go ahead and unmute.
Hi, Anisha. A really nice presentation and very stimulating. Is there a relationship between the wind strength and the chlorophyll layer depth? And does that explain variation in chlorophyll biomass from year to year?
Thank you for the question. Actually, in order to get this modeling, we only choose wind direction, wind speed, and water temperature. And we wanted to work more on the buoy data, because for now we have only taken the buoy data near Muskegon, but it would be better if we get the buoy data over here. So I don't actually know, but since we only model build the regression model based on this variable and focused only on this variable, so I only know about these attributes, but that's something we can look in future.
Thank you.
Thanks for the question, Ed. Okay, looking to see if anything else has come through here. Okay, let's see. Sorry, I think we might have another hand up. Jia Wong has a hand up. Jia, I'm going to allow you to unmute yourself to ask your question. Okay, Jeff, if you want to ask your question, you're able to unmute yourself now. Okay, Joe, you're unmuted if you want to speak. Okay, Joe, we're not able to hear you, so I'm going to re-mute you. Maybe you're having some difficulties on your end with your mic. So Joe, if you have a question, feel free to type it in the chat box and I will read it. And in the meantime, I'm not seeing anything come through the chat, so that he might be unknowingly pressing buttons over there. So we will go ahead and move on. Excellent job, Anisha. Loved your talk and really interesting.